glad to be here. It's my first time at G4G. It's my first time on television, I guess. And it does look like Oscars, like somebody mentioned today. So, Mom, Dad, I love you. I apologize for the long title, so I'll skip that. I'm just going to tell you that this is a piece of work we try to do to formalize the study of regular flexagons with my collaborators Bruce McLean, which presented 2 days ago, and Hua Wang from the Georgia Southern University. I'm just going to go quickly over what a regular hexaflexagon is, which most of you, I bet, know. And then I'm going to discuss the, what's happening behind the faces of regular hexaflexagon. The purpose of what we are doing here is the ultimate goal was to design a model and write a computer program to simulate a regular hexaflexagon of any order. So, regular hexaflexagon, we start with a straight strip of paper. We divide that in equilateral triangles, and we fold the strip of paper along the lines that divides the triangles till we get into a shape of a hexagon. To make things interesting, what we do, we put numbers on each face. We put numbers on the back of each face as well. We put in some colors just to make things more interesting, and we fold everything till eventually gets to the shape of a hexagon. Now, what we see on the very last figure, the hexagon, we see some numbers, and we get to see only what's on the top of the hexagon. What we want to know is what happens behind the first face, and what we want to know is what happens when we scramble the faces of the flexagon. There are many ways of scrambling the faces of a regular flexagon, and actually we've seen some demos the last 2 days, and I'm not going to do that. Well, I'm just going to say that here's a sample of a regular hexaflexagon, and here's a way of, whoops. All right, here's a way to scramble those faces. There's a pinch flex which was introduced by Arthur Stone the very first time when the flexagon was invented, and then Bruce McLean introduced the V-flex in 1963, and the V-flex actually allows to scramble faces of a flexagon well, depending on how many triangles we use, in millions and billions, huge numbers of possibilities. Well, they published a paper a few years ago, and the numbers are really, really huge. They make the budget deficit pocket money. So yeah, we have so many possibilities, but let's see what happens behind the top face. So behind the top face, we see number 1 on the top triangle, and what's behind that, it's a 1 on top, 4, 5, 2, and so on. So our goal was to determine, okay, if we know this sequence of numbers, can we determine not necessarily what's behind, because we know what's behind, can we determine also the orientation of each face? So when we scramble the faces, these triangles rotate in different positions. So in order to build a simulator, in order to create a model, we wanted to determine not only what's behind, but also what is the orientation of each face. In order to do that, we created the state diagram, and we encoded the state of each triangle using a 3-letter code. The face state is given by orientation, up or down, is given by the number, odd, even, and the position of the free edge of the triangle. So when we started with the strip of paper, each triangle had 2 hinges and one free edge. So the orientation of that free edge gives us the first parameter of the state of the triangle. We also define transitions. So as we fold triangles on top of each other, we fold triangles on one position of the hexagon, and we call that the face transition. So we fold faces in the same pile, and eventually when we move to the next position in the hexagon, we call that a path transition. So we build this nice diagram that actually we found that is working for any regular flexagon of any order, which allowed us to actually create a computer model for regular flexagons of any order. Now here's how it works, and I still have time to show you how it works. Let's say we have the numbers we've seen earlier for the face with 1 on top and for the face with 7 on top, which is in counterclock order. So 1 is up, is odd, and it points the small segment that goes from the number. It points to the next position in the hexagon. Face phase 2, which we don't see, which is behind, according to the transitions, is a down, it's an even number, and it points to the previous. We are in the same pile, so we follow a phase transition. We go to number 3, which is up, which is odd, and which is, up, odd, forgot what O is. There's a mistake there.
Wrap up.
We move to number 4, which is in the same pile, is down, even, next. And now, as we move to the next pile, we find 6, which is up, odd, and pointing previous. And eventually, we find 7, which is the top triangle, which is what we display in a computer program, which is up, is even, and it points to the previous. So that O should be actually, well, there's a small, yeah, that O should be the previous. And this is how we determine this is how we create the computer program. I know I'm over time, but this is how it works, and we're able to create a computer program. Thank you so much, and I apologize for the delay.